Or
Good afternoon. I hope that you all enjoyed the first lab on Monday. Reminder that homework number 4 is due at midnight tonight. I believe that question number 6 will be made into a bonus because of some confusion about the correct solution to that problem. And homework 5 has already been posted and is due 12 days from today. Okay, so I'm going to do my best to transfer as much of my knowledge about RLC circuits from my brain into yours. And I will start with a very brief recap of last class. Okay, so we're basically covering 4 different types of RLC circuits. We have series RLC, where all 3 elements are in series, and we have parallel RLC, which you'll see later today, where all 3 elements are in parallel. And then for each of those 2 types, we have either a source-free circuit like this, where there's nothing energizing them, and a step response, where there is something energizing them. And so we did source-free series RLC last class, or we started it last class. And what we saw is that the solution for the current here is the current through the inductor, but of course it's common to all the elements. But strictly speaking, in a series RLC circuit, we solve for the inductor current, whose solution is given by the second order differential equation, which has one of 3 types of solutions, depending on the values of R, L, and C. So if the capacitance is bigger than 4L over R squared, then our polynomial, our characteristic polynomial here, has 2 real negative roots, and we have the solution takes this form. If you happen to pick the capacitance to be equal to 4L over R squared, you get a special case, which is called critically damped, where we have 2 real and identical solutions, so really 1 solution. In which case, the general form takes this shape, takes this structure, where notice that one of the exponentials is multiplied by a linear term. And then the third and last case is where the capacitance is smaller than 4L over R squared. Our polynomial in this case has no real solutions. It has only complex roots. In this case, we have oscillations in the solution for I. So we have a sinusoid whose amplitude is decaying exponentially. And we're going to do one of these examples right now. I'm going to skip over the easy examples, and we're going to move straight to this. All right. So we are asked to find I of t in this circuit, assuming that the circuit is in steady state before the switch goes from the closed to the open position. Okay, so you're basically going to be analyzing the circuit at 3 time points: right before the switch, right after the switch, and at the end of the universe. Okay, so let's look right before the switch, when the switch is in the closed position, right? So here's what that circuit looks like, right? Because we have, notice that this branch is conspicuously missing, right? Because it's an open circuit. A capacitor in steady state is an open circuit. And so you can ignore this branch. And this branch here is just a resistor now because the inductor is a short. So all we have is a very nice simple circuit, series circuit with a battery in parallel with two resistors. And from Ohm's law, we know that the value of this current I, where I is, again, it's the current through this short circuited inductor, is equal to an amp. Whereas the voltage across the capacitor, which is the voltage between this point and this point, which is equivalent to the voltage between this point and this point. In other words, it's the voltage across the 6 ohm resistor, is equal to 6 ohms times 1 amp is equal to 6 volts. So if there's any questions as to how we obtained 1 amp for the current, inductor current, and 6 volts for the capacitor voltage, go ahead and raise your hand virtually or just shout at me. Otherwise, we proceed. Oh, we have a question. Okay, so the capacitor is open circuited. So this is an open circuit, which means there's no current flowing here, so you can just ignore it. And effectively, this V as drawn here becomes the V between this point and this point. And so it extends to the voltage between this point and this point. But this is a short circuit at DC. And so this V is actually the voltage across the 6 ohms when you're looking at time equals 0 minus. Moreover, this I, which models the inductor current, is the I that's flowing through this inductor, which is over here, which is short circuited, right? And so then in this circuit, it's clear that I is equal to 10 volts divided by 10 ohms. And so there's 1 amp flowing here, which is really 1 amp flowing like this, right? That's really what is happening. And so there's 1 amp flowing through the 6 ohm resistor, which means that the voltage across this capacitor is 6 volts, and the current through the inductor here is 1 amp. And now, the nice thing is that those values carry forward to time equals 0 plus, which is here. So at time equals 0 plus, we can ignore the battery and the 4 ohm resistor, right? All we have is an RLC series circuit that has no source. And notice, why do we have 9 ohms over here? Who can tell me how this 9 ohms came up in this circuit?
You added the 3 and the 6 resistors together?
Exactly. Because they're in series, so we can just add them and we can make our lives a lot easier. But now we have this canonical RLC circuit, right? And the reason we can do this here, and we could not have done it in the original circuit with the switch closed, is because now they are in series, because all that's remaining in the circuit is this mesh. Whereas before, we had the battery and the 4 ohm resistor, and they weren't in series. When this switch is closed, the 6 and the 3 are not in series. Okay. So now, let's see, the next step, right? So this is just the explanation of why we combine the 3 and the 6 ohms into a 9. So now let's compute our alpha and our omega. So our alpha is R over 2L. So this is just simple arithmetic. You just compute your alpha, you compute your omega. In this case, alpha is less than omega. That's called the underdamped case. That's when what's inside the square root is negative. And so we have two complex roots. And when we have two complex roots, let me just to give you guys, point you to which equation we're using. We are using, where is it now? This equation here. Okay. So in our circuit, we have alpha was 9 and omega was 10. So we have the underdamped case. So we need an alpha and an omega, which we have. And then we need to solve for our B1 and our B2 coefficient. So that's what we're about to do. We have the alpha, we have the omega, we've determined that we're using this form. So all we're gonna have to do now is find values for B1 and B2. And we get those by using our initial conditions. All right. We are here, right? So we have our alpha. Omega is what's basically square root of 19, which is about 4.4. And now the question remains, how do we compute our two coefficients, which here are termed A1 and A2? Well, so we need two equations. The first equation we're going to get by plugging in t equals 0 into this equation. And that's going to give us A1. Right? So when I is 0, this equation simplifies to A1. And we know, from our initial condition that our initial current has to be 1 amp. And so that tells us the value of A1 has to be 1. So we're almost there. So now we have the value of A1, but we still need the value of A2. So the way that we get A2 is by getting the initial derivative of I. Right? So if you recall last class, basically, maybe I'll just derive this. And maybe I'll try to draw over top of this at my own peril. So we had an R, an L, and a C. Hopefully I don't screw this up. And we're going to write the KVL around this loop at time 0. So the KV, and this is my R, this is my L, and this is my C. So we have V of R plus, let's say L, and let's just call it, right, and we're evaluating this at time equals 0. So we have VR is just R times I 0 plus L times and now let's, this is a prime. Now let's isolate I prime 0. So I prime 0 is going to be equal to negative, we're just going to stick the negative sign, RI 0 plus BC 0 over L, basically. Okay, and so what this equation is saying is that if I know the initial value of the current and I know the initial value of the capacitor, I can use that to get the initial value of the derivative of I, which is really important because I don't have to, I can get the initial value of the derivative just by looking the initial values of the inductor current and capacitor voltage. Okay, and so that's what I'm using over here. This equation here, that's what I just had up on the annotation. And so if I know that my initial inductor current was 1 amp, and I know that my initial capacitor current was 6 volts. And so I plug that into this equation and I have an initial value of the derivative of I. And it turns out to be -6 amps per second. And so now I can go back to this equation. I can take its derivative. So apply it's basically the product rule. So I differentiate the exponential and leave the sinusoid alone. Then I leave the exponential alone and I differentiate the sinusoid. And when you evaluate this derivative at t equals 0, a lot of things drop out. Anything that's sine drops out because sine of 0 is 0. Anything with a cos becomes 1, and the exponential becomes 1. So you get basically -9 sorry, times A1 plus omega, this is the omega d, times A2, right? And so, and we know that A1 is equal to 1. So we can just use this equation to solve for A2. So now we have everything we need. And we can substitute our coefficients of A1, 1, and A2 is 0.688. And so just, I'm going to do a couple of these, step by step with my trackpad. But I just want to if anyone's unclear as to what we did to get the coefficients, the first step to get the coefficients is to evaluate this function at time equals 0. So then the cos becomes a 1 and the sine drops out. And then you get that A1 is equal to I of 0. And in this case, I of 0 was equal to 1 amp. To get this, to get your in the second step, you differentiate this expression and you evaluate it at 0. And that has to equal the initial derivative, which we got by applying KVL to our RLC circuit at time 0. So this will take some practice, I believe, to kind of to ingrain itself in your brain. Just once you've practiced on a few of these, this will all kind of, I hope, crystallize. And to kind of try to demonstrate that, I will do this example here with you. Okay, so we have a circuit that has on the left side a battery in series with a resistor. And on the right side, we have an RLC circuit. And we are asked to find I of t. Okay, so the first thing that we're going to do, as always, is to, well, it's actually time equals 0 minus. So what is the value of I0 excuse me, I0 in this picture. When the switch is in position A, and this circuit has been in steady state. So in other words, this inductor at time equals 0 minus is a short circuit. So what is the value of I of t, of I of 0 in this? Yeah. Excellent. Thank you, Christian. Yes, it's 5 amps. Oh. Don't want to do that. All right. That's it. I'm going back to the scratch pad. So it's 50 volts over 10 ohms is equal to 5 amps. Now, what about the initial value of the capacitor voltage here? What is the value of the capacitor voltage V of 0? In this circuit. So in this picture here, with this switch with the switch at position A, what is the value of V? Zero. Excellent. 0 volts is correct. Oops. I did it again. You're probably too young to know that. Okay. 96 was a good year. Let's see. And let's get my cursor back. And let's get the, let's actually use this. So we're gonna have that I prime of 0. This is that equation that I showed you before. Square brackets here. So this is the equation that we want to use. And so in this case, I prime of 0 ends up being negative 1 over L is just 1 times, and then the R in this circuit. So keep in mind that the RLC circuit is over here, not over here. And so the R that we're working with is 5. Very important. And the I0 is equal to 5. So this becomes 5 times 5 plus 0 is equal to negative 25 amps per second. So that's our initial, we have an initial condition on the I and on the initial condition on I prime, which is nice. All right, so now let's draw this circuit at time equals 0 plus. And what you will see is that the circuit now loses its source, so it becomes source free. So it just becomes the inductor, the resistor, this is 5, this is 1 over 9, and this is 1. So this is just our standard RLC circuit. So now we have to define our alpha and our omega, right? So alpha is equal to R over 2L. So in this case, R is equal to 5 and L is equal to 1. So alpha becomes 2.5. And our omega is always 1 over the square root of LC, which is equal to, so this, what's in the square root sign is 1/9 times 1. So the square root of 9, because it's, let's see. Yeah, this, it's, no, the square root of 1/9. 1 over the square root of 1/9, it gets garbled in my head. So I believe it's like this. I believe is equal to 3. Which means that we have an underdamped circuit with omega d so omega d, remember, is just equal to omega naught squared minus alpha squared. And here you'll need a calculator, and that's why you will be allowed a calculator on the final exam. The answer is 1.6583. Okay, so that's our omega d. And so our standard form of the solution that we're going to be using is times, and what's in it is A1 cos. I'm just going to call omega W, even though it's not really a W. Okay, so this is our general form. And we already know that alpha is equal to 2.5, so we have alpha. And we have W, we have omega D, which is 1.6583. So now what we have to do is find the value. Actually, let me plug them in to kind of -2.5t times A1 cos 1. I'm just going to call it 1.66. Okay. So that's our solution with the alpha and omega filled in. So now what we have to do is evaluate this equation at time equals 0. So what happens, let me ask you, what happens to the highlighted equation when I set t is equal to 0?
You just get A1.
A1, excellent. So that becomes, so I of 0, we got, remember I of 0 was 5 amps, is equal to A1. Okay, so that's our first, that's how we get A1. It's very straightforward in the underdamped case because everything drops out except for the A1 term. Now, what about the derivative? This one's a little bit more, simplification, because you have to take the derivative of this function and then set it to 0. And so I'm just going to tell you that it works out to be -2.5 times A1 plus, and you can, if you just want to memorize this, that's fine, that it always works out being negative alpha times A1 plus omega D times A2. And the way you get that is by applying the product rule to this equation. Okay. And so let's now, let's rearrange this to solve for A2. Okay. And what you'll see is that A2 is equal to, let's see, let's put this all in square brackets. I prime of 0 plus 2.5 times A1 over WD. And we have that I prime of 0, we already had, was equal to negative 25 amps per second over here. And finally, we have that when you plug in the numbers here for, if you plug in negative 25 for I prime 0, and you plug in 5 for A1, you get negative 5 plus 2.5 times 5. So I think negative 12.5 divided by 1.6583 gives you about negative 7.5378. Okay, and so our final solution, which I'll put here in color red, IT is equal to exponential negative 2.5 t times 5 cos 1.66 t minus 7.54 sine 7.66 t. Okay, so remember, this is the underdamped solution, right? So this part here is a sinusoid. So the sum of a cosine and a sine looks very similar to a sinusoid. And this is a decaying exponential. So you can think of this as a sine function whose amplitude decays over time. All right. Hopefully that wasn't too painful. Clear that. This was the equation. This was the solution that we just derived. All right. So we've completed 1/4 of the material in lecture 8. Like we have source-free series RLC, which we just did. Now we're moving on to source-free parallel RLC. And the good news is that all of these are all similar, but if you know how to do source-free series RLC, it's very straightforward to be able to handle source-free parallel RLC. So what we have is a circuit that has a resistor, an inductor, and a capacitor all in parallel. Okay, so in other words, the resistor, the inductor, and the capacitor are all sitting at the same voltage. And what we're going to assume here is that we had a battery connected to this node. We had a battery that was maybe here. And so the capacitor is charged up. The inductor is shorted. It's got current flowing through it. And suddenly we remove that battery. And then something's going to happen. Namely, there's going to be a redistribution of the energy in this circuit. And you're going to have, whereas in that steady state, when the battery is connected, so let me actually draw this because this probably would have been useful to have in the course notes. So if you had a battery here, this is actually a good question for you guys. Let's say I have a battery, a 5-volt battery, connected like this. How much current is flowing in each of these branches here in this picture? We have a 5-volt battery is connected to this RLC network. Who can tell me where the current's flowing in this? And assuming that nothing's changed in a very long time. So we already have an answer. 5/3. That's a valiant effort. Goes through, yeah. That's right. It's all going to go through the short. Even though there is a resistance here, this circuit here, let me see, oops. So if I draw kind of a thick dark line here like this. If I short this inductor, then nothing's going to flow through the resistor. And this is an open circuit, right? This is an open. So this completely comes out. And basically the current takes this path, right? So that's where we are right before time zero. And then at time zero, oh no, my cursor. Okay. Get my cursor back. Sort of. And so when that battery is disconnected, all of a sudden there is going to be current flowing here, and there is going to be current flowing here. There's going to be a redistribution of the energy. And that's really what we're talking about in this source-free parallel RLC circuit. So let's see if we can come up equations for the voltage across the current, for the voltage across these three elements as a function of time. Okay. The obligatory statement as to why we're teaching you this. It's a pretty classical result, actually. I think I know my daughter is covering this in her physics class, so I think they may teach you this in physics. And so we assume that we have an initial capacitor voltage V. One of the kind of key points here is that our solution, the solution that we're going to be solving for, is really the capacitor voltage. And once we have the solution for the capacitor voltage, we can use it to solve for the other elements in the circuit. Yeah, I think she would say the same. Actually, I'm not so. She said that RLC circuits were some of the easiest stuff that she had in her physics. I don't know. I also had a really hard time with physics in undergrad. Although I now as an old person that can just read about whatever I want when I want, I enjoy physics a lot more when I'm not burdened with the with exams and labs. So anyhow, I digest. So let's apply KCL at this node. Okay. The sum of these three currents has to equal to 0. So the current through the resistor is V over R, Ohm's law. The current through the inductor is the integral of V divided by L. Remember that this is the equation for the current through an inductor. And then the current through the capacitor is equal to C times V prime. So hopefully everyone follows this. This is like your starting point. And so now if you take the derivative of this function, you get this function. The derivative of 0 is 0. And so you get a second order differential equation. And you can rearrange the terms so that the second derivative has a coefficient of 1. So once again, as before, you can just think of this as a quadratic equation, where this is the square term, this is the linear term, and this is the constant. And as before, we have a characteristic polynomial. The only difference now is that alpha is not R over 2L, it's 1 over 2RC, because this is a parallel RLC circuit. So the value of alpha is, you have to kind of memorize this, unfortunately. So the value of alpha is 1 over 2RC. The value of omega is the same, 1 over the square root of LC. And so once again, we have the three cases. When alpha is bigger than omega, you get the overdamped case, where you have two real negative roots. And so S1 and S2 are the roots of your quadratic equation here. S1 and S2 are, so S1 is negative alpha plus square root of alpha squared minus omega squared, and S2 is equal to negative alpha minus the square root of alpha squared minus omega naught squared. The second case is the critically damped case, when alpha is equal to omega. That's when what's in the square root is equal to 0. And the only solution here, the only root, is negative alpha. So here the trick is that you multiply your second coefficient by a linear function to get a valid solution to your original differential equation. And lastly, when alpha is less than omega, you get an underdamped response where you have we have a decaying exponential multiplied by a sinusoid. This is the same as before. The only difference is the nature of alpha. Before it was R over 2L, now it's 1 over 2 RC. That's it. Everything else stays the same. So the constants are determined as before from the initial conditions. So we know we can directly solve for the value of V naught. Now comes the trick. So how do you get the initial value of the derivative? Well, I'm going to try to draw it to kind of convince you as before. So we have our inductor, our resistor, our inductor, and we have our capacitor. And let's consider this at time equals 0. And let's write the KCL equation. And we get that V0 over R plus I0 plus CV prime 0 is equal to 0. The CV prime is the current through the capacitor. And so the reason I'm writing this out, there's my cursor again. At least I have a systematic way of getting it back now, even if it is extremely annoying. And so V prime, if I rearrange this equation for V prime 0, I get, let's see, it would be V, let's do it, 0 plus R I 0 over C. I think this becomes negative. Right? So I can solve for V prime of 0 if I know the value of V0 and I0. And importantly, I0 is defined as the current through the inductor. And V is here, right? And this is also V. Okay, so V over R is here. I is here. And CV prime is here, right? So the sum of these three currents, current 1, 2, and 3, have to equal to 0 because there's no source. And then you can use this equation to solve for V prime of 0. And I'm taking the time to show this because this is a point of confusion in the past where people don't remember how to get the initial value of the derivative. This is how. Just apply KCL at time 0. Okay. Now I'm about to show you that in the slides, right? This is the same thing. And so the initial value of the derivative of V can be obtained from the initial value of the voltage and the inductor current. In other words, if you have V naught and you have I naught, you can get the initial derivative of the capacitor voltage, which then will give you the two equations that you need to solve for A1 and A2. Okay, so remember, we are solving for the capacitor voltage. And once you have the capacitor voltage, you can use it to solve for the resistor current or the capacitor current. So remember, in a series RLC circuit, we are solving for the inductor current because in a series circuit, the current is common. For a parallel RLC circuit, we're solving for the voltage, namely the capacitor voltage, because the voltage is common to all three elements. All right, I'm going to skip to these examples. These examples are just like, they give you values of R, L, and C, and they ask you to find alpha and omega. I'm very confident that you guys are able to plug in numbers into formulas, so I'm going to skip it altogether. And you're going to see this anyways in the equation. I'm going to skip all this for the sake of time. All right, we're going to do, let's see, do I want to do this? Yeah, I'm going to do this example, and then I'm going to do I'm going to do one for you. So first of all, what do I want to do? Let's look at this. Let's look at the circuit. First of all, why is this in the parallel RLC section of the notes? Well, if you notice that after time equals 0, this switch goes from the open position to the closed position. Right, so this is, I'm going to talk about this now because this has caused a ton of confusion. What happens? I'm going to draw this circuit out. Oh, crap. So I have a battery. I have my resistor. Let's say the switch becomes closed, right? And let's say that so my question for you guys is, let's see, how do I do this? What is the relationship between this part of the circuit, the left, and the right? It's kind of an advanced question, but I want to talk about it now because before you get confused by what you see on the next slide. So, in other words, how much of the battery do these three circuit elements sense? Yeah, exactly. That's excellent, Omar. They are absolutely independent. Whenever you encounter a situation like this, you can basically separate this into two circuits, where one circuit is just the battery and the resistor, and then the other circuit is the RLC. You can for all intents and purposes make them completely separate. Why? Well, consider any current that comes out of the battery and goes through the left resistor, right? All of it is going to come back here. It's not going to go through here because it has a short circuit path back to the battery. So it's going to ignore, the current from the battery is going to ignore everything over here. Similarly, let's say that magically some current appears through the inductor, right? And it gets here. It's going to go this way. It's going to take the short circuit path. It's not going to go through a resistance when it doesn't have to. And so what this means is that these two circuits are completely decoupled. And you do not have to worry about this capacitor sensing this battery. It will not sense it. It's as if it doesn't exist. Okay, so that's something that we're going to see once this switch goes from the open position to the closed position. But right now, it's still open. And in this configuration, this capacitor does sense the battery, right? Because there is no, without this short circuit in place, the battery is very much sensed by the capacitor. So how do we get an initial, so we always start off by getting the initial values for the capacitor voltage and the inductor current. So now let's short circuit the capacitor, right? Oops. So we're just going to short circuit this, and we're going to open circuit. I don't know how to draw an open circuit well, but we're going to open circuit the voltage here. So what we essentially have is a battery, the 30 ohm resistor. Oops, a particularly hideous looking resistor. This is a 30 ohm. And this is 50. And this is our open circuited capacitor. And our I is defined this way. And this is 40 volts. So in this picture, the value of V is obtained by current by voltage division, right? So you have our 40 volt battery, which is divided across the 30 ohm resistor and the 50 ohm resistor. So is equal to 5/8 of 40 volts, which is equal to 25 volts. Hopefully everyone, if you're not clear on how we got this 25 volts, please, you know, oops, please do not be afraid to speak up. Okay. All right. So then the next part of this initial condition is the inductor current I. So in this circuit, basically the current is flowing this way. So we suspect that the value of I is going to be negative, right? Because this is the positive end of the voltage, this is the negative end. So we know there's 40 volts divided by 80 ohms flowing clockwise. So when defined counterclockwise, there's going to be negative half an amp flowing through the short circuited inductor. Okay, so hopefully everyone understands how we got an initial capacitor voltage of 25 and an initial inductor current of negative 0.5. All right. So what kind of a, this is going to be, and this is why I talked about, I'm not particularly thrilled with this picture. To me, it causes more confusion than anything, but what this picture is trying to show is that these two circuits are decoupled. Right? So that's what I was going on about previously. That the RLC circuit here does not, it's separated from the battery and the 30 ohm resistor. The last bit of initial conditions, though, actually that I forgot to talk about is the initial derivative of the voltage. So remember how we derived an expression for the initial value of V prime as a function of V naught and I naught. So we simply plug in our numbers. So remember, the R here is the R in the RLC circuit, which is 50. The C is 0.4. Sorry, the C is 20 microfarads, and the L is 0.4 Henry. Okay, so we plug in a value of 20 times 10 to the minus 6 for the capacitance when evaluating this. And so remember, just if you forget where we got that, we got it from this equation. All right, this is by writing the KCL equation at time 0. We get this expression, which allows us to solve for the initial derivative as a function of the initial values. Okay. We're here. So now we have our alpha, which is equal to 1 over 2RC, which works out to be 500. And we have our omega, which is 1 over the square root of LC, which ends up being 354. So when alpha is bigger than omega, we have the overdamped solution, which is the one where the quadratic has 2 real and negative roots. And those negative roots in this case, which are obtained by evaluating just a quadratic equation, are negative 854 and negative 146. So those are the values of the 2 roots, which we can simply plug in, over here. Negative 854 and negative 164. So once we have the roots, all we need to solve for are A1 and A2. And we solve those by plugging in the initial value of V and then the initial value of V prime. So if you substitute t is equal to 0 to this equation, you get that V of 0, which we know is equal to 25. Remember, all the way back from voltage division, that the initial value of this capacitor voltage is 25. So now that we have the general form, we can plug in t is equal to 0 and identify that A1 plus A2 must be equal to 25. Right? Because these complex exponential terms converge to a value of 1. And so we have one equation, 2 unknowns. So we need one more equation in A1 and A2. Excuse me. And so to get that second equation, we differentiate this general form. And we get negative 854 A1 times e to the negative 854t minus 164 A2 e to the power of negative 164t. So let's simply plug in a value of t is equal to 0 to get rid of these. And we get that 0, which is our initial condition on the derivative of v, must be equal to negative 854 A1 minus 164 A2. So now I have one equation and 2 equations. So we can solve for A1 and A2. And once we solve for them, we plug them in to the general form of the solution. All right, I'm going to just take a sip of my water, give you guys a chance to ask questions if you have any. Okay. All right. For those of you just waking up, we are doing parallel RLC circuits without a source. And the next one I'm going to do on the slide. So let me try to not go into full screen. Okay, let me try this to give myself more room. Oh, all right. We are asked to find V of t, where V is defined as the voltage across this capacitor. So the first thing, as always, is to draw this circuit at time equals -0. So and this one is easy to draw, fortunately. Why? Because, well, it's just the current source and the switch, right? So the current source is here, because the switch doesn't happen until time equals 0. So right before the switch, we have a current source in parallel with a resistor, in parallel with an inductor. Actually, I should have drawn this. I'm just going to draw this. Okay. This is defined as V. I'm going to call this, by convention, I'm going to call this I. And this is 2 amps. Okay, so who can tell me the initial value of V here in this picture? In the picture that I just drew. We have an audience answer. 0 is correct. The initial value is 0, right? And the reason it's 0, because it's parallel to a short, right? So our capacitor voltage, our capacitor, which is an open circuit, is parallel with a short circuit. So it has to have a value of 0. By definition, a short circuit has, actually, see if I can use my eraser. Oh yeah. What about the value of I at time 0? What is the value of this current here? So it depends on where V is defined. Yeah, well, in these questions, yes, the V will always be the capacitor voltage. And yes, Mohigul, that is correct. The answer is 2. Because all of this current source will go through the short. So the current will just go through like this. It will skip the resistor. And so I will erase. Oh, didn't mean to erase all that. So V0 is equal to 0 volt and I0 is equal to 2 amps. And I also want to get an initial value for V prime 0. And remember from our previous equation, it was equal to negative RI0 plus V0 over RC. So in this case, V0 is 0. So this term drops out. And then R times I0 is negative 40 over 20 times C, 20 times 0.004. Let me just expand this. You'll just have to take my word for it that the value of V prime 0 is equal to negative 500 volts per second. So it's a large value. In other words, the capacitor voltage is rapidly changing at time 0. That's what this equation is saying. Okay, so remember that this equation that I just used, that I'm not able to highlight anymore, but it's over here, is obtained by applying KCL at this node at time 0. And so we have everything we need now in terms of the initial conditions. Now what we need to do is to figure out our alpha and our omega. So let's figure out our alpha. which is equal to alpha, is equal to 1 over 2 RC. Which here ends up being, let's see, 1 over 2 times 20 times 0.004, which is works out to be 6.25. Okay, and our omega naught is equal to 1 over the square root of LC. So the value of L is 10. So it becomes 10 times 0.004. And when you work this out, you get a value of 5. Just, I believe, yeah, you get a value of 5. It becomes 1 over 0.04, so 1 over 0.02, which is 1 over 0.2, which is equal to 5. All right, so we have our values of alpha and omega. So since alpha is bigger than omega, our solution is overdamped. In which case, we know that our solution becomes V of t is equal to A1 exponent S1 times t plus A2 exponent S2 times t. So this is our general form, and we're about to solve for S1 and S2. So here's where you do that quadratic equation. So we know that S1 and S2 are equal to negative alpha plus minus alpha squared minus W naught squared. Okay, and in this case, it turns out that S12 is equal to negative 2.5 and negative 10. So they're always going to be negative. Just remember on an exam, if you get negative root, if you don't get negative roots, if you get real and positive roots, you've made a mistake somewhere. These roots will always be negative. Okay, so these are our two roots. And so now we can plug in them into the general form. And we have that. So we're almost there. Now, the last step is to basically take this and plug it into here, and then take this and plug it into here. So we're gonna have two, we need to find A1 and A2, and we're gonna get them by plugging in these values. Okay, so for example, phi of 0 is equal to A1 plus A2 has to equal to 0, which means that A1 is equal to negative A2. So since the sum of, when the sum of two numbers has to equal to 0, it means that the two numbers are just negatives of each other. And then for V prime of 0 ends up being S1 times A1 plus 2. And that's equal to negative 2.5 times A1 minus 10 times A2. And that has to equal to negative 500. And so when you solve these two equations simultaneously, this equation and this equation, you get the A1 is equal to negative 66.2 and A2 is equal to positive 66.2. Okay. So now we can write finally our final answer, which is that V2 is equal to 66.67. And then here's where we can put we can take that as a common factor and write exponential negative 10t minus exponential negative 2.5t. Okay, and that becomes, see what color I not used yet. Okay, this becomes the final answer. Okay. All right, how about this shade of purple? Yeah, that looks nice. Okay. I know some of you must be feeling not great about this, but I assure you that once you actually sit down and work with these problems, one of the things I always tell my daughter, what you should do is when you want to practice this material, watching these lectures, I doubt is going to teach you the material. I think that what's going to teach you the material is if you open up the slide, cover up the solution, and try to reproduce it on your own. And if you get stuck, watch a little bit, try it again, and do that. You know, basically, that's the way I would prepare. I would try to reproduce the solution that I saw in my course slides by myself. And if I couldn't do it, I would look at the solution, and then the next day, when I had forgotten it, I would try to reproduce it again. And I would do that until I was able to reproduce it. And that's really the only way you're going to learn this. I don't believe that, I mean, most engineering courses, and especially circuits, cannot be learned by watching someone else solve the problems. It's just, unfortunately, our brains just don't work that way. There's something like we develop a false sense of confidence when we watch someone else solve the problem. Somehow, or like we just tell ourselves that, okay, I understand every step, and therefore I understand the material. But I think that that's a mistake. Being able to follow the solution is not the same as actually being able to derive it, you know, on your own, without all the material in working memory. That's the other thing. All right, where are we? Doing okay. Let's start step response. And let's see. Well, let's see where we are after I get through the theory. So step response, fortunately, is not that much different from source free. What you will see is that the solutions that we have been deriving to this point for source free circuits are a major component of the step response solution. And so we have a circuit such as this. And so first of all, how do you know that this is a step response and not a source free circuit? Well, the way you know is that this battery is energizing the RLC circuit after time 0. Okay, so after time 0, the RLC network is being driven by the battery. And so it's not source free. And if it's not source free, we know there's a step response because up until 0, there's no source, and after time 0, there's a source that stays on forever. So once again, from first principles, what we're going to do is to derive a KVL equation for this circuit. So because it has a common current I, we're going to express our KVL in terms of I. So the voltage drop across the resistor is equal to R times I. The voltage drop across the voltage drop across the capacitor, we're going to call V. And the voltage drop across the inductor is by definition equal to L times the derivative of I. And those 3 voltage drops have to equal to the battery voltage. Right? So this is just the application of KVL to the circuit. And we also know that the value of I is equal to C times the derivative of V. Right, so the V is going to stand for the capacitor voltage, and I is going to stand for the inductor current, as always. And notice that the inductor current is shared by the other elements. So now what we're going to do is we're going to plug in this into here and here. And what we get is a second order differential equation in V. So I think one kind of confusing thing is that when we are doing series RLC source free, we were solving for I. And now we're doing series RLC step response, we're solving for V. The good news is that at the end of this lecture, we're going to just give you a prescription for solving any RLC circuit where you don't need to memorize, kind of you don't have to memorize this equation, basically. We will give you the tools to be able to take any RLC circuit and generate a solution. Okay, so first of all, how do we get here? Well, we got here by plugging in I is equal to CV prime into the I terms here. And then we rearrange, we basically divided through by L and by C. And so we have a second order differential equation in V is equal to some constant. So it's not any different than what we saw before. So instead of being equal to 0, now that differential equation has to equal to some positive, some number. It doesn't have to be positive, actually. Although V of S will generally be a positive number. So the way we're going to approach coming up with a solution for V of t here is to break up the solution into 2 parts. One of the parts is called the natural response, and the other is going to be called the forced response. Okay, so the forced response is the response of the circuit to this battery. And the natural response is the response of the RLC to just the transient, basically. So just the switch between battery disconnected to battery connected. Right, so this natural response is a transient response, only true for a short amount of time, whereas the forced response is true all the time. And the nice thing is that you already know how to solve for V of n. It's just using the same techniques that we have been working on since the beginning of lecture 8. And V of f, you're going to see, is just going to be equal to V of s. Okay, so the recipe for deriving the natural response is to disconnect the independent source. So in other words, in this picture, disconnect the battery and solve the circuit. that becomes your natural response. So it's like the source, it's exactly like the source-free case. Okay, so if you had a current source in here, you would open circuit the current source. But since we have a voltage source, we're going to short circuit. We're going to set its value to 0 and then solve for V. And that's going to be our natural response component. Okay, so as before, we're going to have the three cases. We're going to have the overdamped case, the critically damped case, and the underdamped case. And these will depend on the values of R, L, and C, and specifically the values of alpha and omega. Okay, so the only new part, the only new bit to this solution is that the forced component is by definition equal to the capacitor voltage at time equals to infinity, which is equal to the battery voltage. And let's look at why. So in this picture, imagine that the capacitor is an open circuit and that the inductor is a short circuit. Then essentially, all we have in this picture, try to draw this, is at time equals to infinity, we have our battery, our resistor, our short, and our open. And so V is equal to Vs because there's no voltage drop across this resistor because there's no current here, right? So the current through the circuit has to equal to 0. And so there's no voltage here, which means that V is equal to Vs. All right. So we have the three components to the equation, and our forced response is just equal to the battery voltage. So then our final solution is the sum of the natural response and the forced response. So the only difference is that we're adding this V of S here. Everything else stays the same. And now when we evaluate when we're solving for our A1 and A2 coefficients, we have to plug them into this equation. We have to include the V of S because that's part of our initial conditions. Okay, so to get our coefficients A1 and A2, we plug in our value for V naught and V prime naught. And again, notice that here we are solving for the capacitor voltage. So once we know the capacitor voltage, we can get the current through the whole series RLC circuit, and we can get the voltage drops across the resistor and the inductor. But again, as always, you don't touch any other elements until you have a solution for your capacitor voltage. And when we do parallel RLC, you don't do anything until you have your solution for the inductor current. So another way kind of viewing this, and this is kind of a foreshadowing what's happening at the end of this lecture, is that in general, if you're solving for a quantity x of t, that quantity can be broken for a step response. That quantity can be decomposed into these two parts. One is the forced component, and the other is the transient component or the natural response. Okay, so to get xf, you just have to solve for x at time equals to infinity. And to get the natural response, you disconnect all your sources, your independent sources, and you solve for x. All right, so I'm actually, this example is, it's tedious, it's cumbersome, and I'm actually gonna get you guys, just because we're short on time, and I don't think the PowerPoint works great. You can see that it's very lengthy. So I'm gonna go through an example, the practice problem that follows. The only thing I'm gonna say is that basically the process here that we're taking is the same. We're solving for V and I before 0. And then we propagate those solutions forward in time. And let's talk a little bit about the plot. So the 3 cases will look different. If you plot V of t as a function of time, you will be able to distinguish what kind of solution you had. So the underdamped case is the one that has the oscillatory component. And the critically damped case is the one that takes the longest to decay. Now notice that unlike before, in the source-free case, these voltage traces are not converging to 0. They're converging to the forced response. So they are converging to a value that's not equal to 0. So that's important. All right, last thing I'm going to do here, I'm going to at least start this problem. I'm not sure if we'll be able to get to this, not sure we're going to be able to get through to the end of it, but I'm going to try to get as much as I can. I'm going to try to go slowly just to kind of illustrate the concepts. I'll take a sip of water. Okay. So we are asked to solve for V of t, which is defined as always as the capacitor voltage. And we're also asked to solve for VRT, but we're going to leave that part until the very end. Mainly what we're interested in is V of t. So we are told that the switch goes from position A to position B at time equals 0. So the first thing I'm going to do, I'm going to try to get some help here. So what is the value of the capacitor voltage here when the switch is in position A? And I'll give you a hint that it's equivalent to the voltage between this point and this point. And remember that before that switch flips, this is an open circuit. Right? When the capacitor is an open circuit and it's in parallel with the 2 ohm resistor. So what is the voltage? Well, if you just consider this. Eight volts, excellent. That's very well done. B0 is absolutely equal to 8 volts, right? And the reason is because of voltage division. Okay, so V at 0 minus is equal to V at 0 plus is equal to 12 volts times 2 over 1 plus 2 is equal to 8 volts. Right, it's just voltage division of this battery across the 2 ohm resistor. Right, so we have, because this capacitor is in parallel to the 2 ohm resistor and it's not drawing any current because it's open circuited. So let me see if I can now erase. Now let's see what else did I want to solve for in this case. I also wanted to solve for the initial value of, even though it's not drawn here, I want to solve for the initial value of the capacitor, of the inductor current. Right. And it also at time equals 0 minus. So what is the value of I at the inductor current at time equals 0 minus. So in this, you're looking at this picture exactly as is actually, right? And what I can tell you is that the inductor is going to be a short circuit and the capacitor is going to be an open circuit. So how much current is flowing through this inductor when the switch is in position A? Oh, multiple answers. This is my lucky day. Yes, Omar and Hannah, that's awesome. Both of you are correct in thinking that the answer is 0, which it is. It has to be 0 because there is not a complete path for the current to flow. So indeed, we have that I0 minus is equal to I0 plus is equal to 0 amps. And the only thing I'll point out is that because when this switch flips, so now let me draw this because this is maybe less clear. So now let's look at time equals 0 plus. Okay, and we still have our capacitor, and now we can't assume that the capacitor is in steady state. Can't assume anything because the switch has just flipped. We have this picture. And we have no current flowing here. And so the reason, and we have 10 volts over here still. And so there's no current at this moment in time. There's no current flowing through the inductor. And that's important because we need that to get an initial condition on V prime. Remember V prime, so I should just label V prime in this picture as well, just to be clear. V is equal to here, right? And we know that CV prime is equal to I, and that holds also at time equals 0, which means that V prime of 0 has to equal to 0 volts per second. So that's very important because now we have an initial condition on V and its derivative. All right. So this is an RLC. This is a series RLC circuit with R is equal to what? What is the value of R in this RLC circuit that we're considering? Excellent, Jonathan, that's great. It's absolutely equal to 10. Oh, I lost my. Okay, so R is equal to, let me just erase this. So this is a series RLC step response with R is equal to 10, L is equal to 2.5, and C is equal to 1/40. And we also know that alpha is equal to R over 2L is equal to 10 over 2 times 2.5 is equal to 2. And we also know that omega is equal to 1 over the square root of L times C. So 1 over the square root of, let's see, 2.5 over 40. And when you do the arithmetic, works out to be 4, okay? And so we have we know that this is an underdamped. Oops, I'll just draw this. Then solution, meaning that V of t is equal to, and remember now we have the forced component plus gonna have exponential negative times t times, say, a1 times cosine omega d times t, and I'll unpack this in just a minute, times sine omega d times t. Okay, so this is, it's a lot, right? So let's see if I can get this all in the one line. Yes, just barely. Okay, so first of all, how did I get all of this? So I'll try to highlight this. This here that I'm highlighting, that's our natural response. Okay, that's V of n of t. And that's our natural response. So that's basically the part of the response that only is driven by the switch from position A to position B. And this is our forced response. Okay, so our forced response is the part of the solution that is driven by the 10-volt battery. Right, so there's two different things at play, and they have a different effect on the thing that we're solving for, which is the capacitor voltage. There's a transient that occurs when this switch goes from this position to this position, and that manifests as this term. And then there's just the contribution of the 10-volt battery. And what I can tell you is that V of F is just a constant. It's always going to be a constant for a step response. And its value is going to be 10 volts. Okay, I'm going to stop here. I'm not going to finish this problem today. I'm actually pretty happy with how much ground we covered. The good news I have for you is that we are not too far off from finishing this lecture. And lectures 9 and 10 are much more accessible than lectures 7 and 8. And so it's really, this is the apex of the course is what we're doing right now. It's not going to get, more computationally involved than what we have now. Okay, hand in your homework before midnight tonight, and I will see.
So I think like for the homework, I went through some of your submission for question number 6. I think I sent Dr. Domojowski an email before class today. So like there seem to be multiple ways to solve for question 6. So like we will consider that question as a bonus question. So if you do it, it would be like nice for you. If you don't, that's fine first. And like there are 2 ways to get it. If you do it either way, you will get full credit for that question as well. So just so you know.
Yeah, exactly. So it's essentially a bonus question, correct, Sam?
Yeah, like I think like in your original like there was like another bonus question from your previous year homework, but since you took it out, so I think it's better for us to consider that question as a bonus one.
Sure. Let's do that again.
Okay.
So you can get full points without doing that question. Let's put it that way. And I'll try to come up with an unambiguous solution in the meantime. And then after you hand in homework 4 before midnight tonight, start working on homework 5. So homework 5 covers lecture 7 and 8, which will be on the final exam. So I'll tell you now what's going to be on the final. You're going to have two in terms of the problems, 2 problems from lecture 7 and 8, and 2 problems from lectures 9 and 10. There's nothing from lecture 6 that's going to appear in the problems. You're going to have to use the concepts from lecture 6 to solve. I don't know yet what time. I don't know. I have to check the schedule. I mean, I always go based on what the college tells me to go with. So it could very well be May 24th. The last day of class is the 17th. Okay, that's all I'm gonna say.
Yeah, so one more thing. So for question number 4, where you have to design the circuit, just make sure that you like state clearly the relationship between the resistor, the pair resistor, like, and how they meet the condition in stated in the problem to get the full credit. Like you can not just like show the circuit without like stating the relationship or the number. Either give the number clearly or the relationship between the resistor two-way. Yeah, I think that's all I have to say for this homework. I went through some of your submission and just to make sure that like the like equal opportunity for you guys to get the full credit for like each of the question.
Sounds good, Sam. That's excellent. I totally agree with show your steps when the question is to design a circuit. Unless you're 100% confident that you've got the circuit that will do what is being asked for it to do. Show your steps and justify in words, if possible, also why you made the choice. All right. Thank you for those of you that hung in there till the end, and I wish you all a pleasant weekend.